I got the 0%.
All right, we ready? Ish, ready-ish. We will use a calculator a bunch today, so go ahead and get it out if you brought it with you. All right, so thinking of our things coming up, we're going to do an individual quiz today covering like a question from chapter 5 and most of it from chapter 3. Your exam 2 is a week from today covering chapters 9, 10, 3, and 5. There's chapter 3 homework due tonight and Wednesday night. No homework on Friday, because in theory you are all studying Friday night. Just kidding, probably not. But at least you won't have homework Friday night. We'll review in class on Friday. So as you start working through the end of it and start studying for the test, either email me a question that you come across or just bring the class on Friday and we'll work through whatever questions you may have. Sure. So we're going to review in class on Friday. So as you're studying and you come across something, you're like, man, I wish we did more practice on that. Either email me. It's easier if you email me because I have better example problems. Or just bring the class on Friday and we'll just do it all together. All right. So where we left off on Friday is we looked at mass percent in acetic acid, and we figured out the concentrate or mass percents of carbon, hydrogen, oxygen in acetic acid. I'm gonna come back to this slide. I want to do one other thing, and then it'll make more sense. This double-sided slide thing has messed me up. I want to do determining chemical formulas, and then we'll do conversion factors. All right, so you may be thinking last Friday, it's a really random thing that you would know the formula and then want to figure out the mass percent. That's real weird. No one ever does that, except in here. That's the only time that'll ever happen. More likely is you will make a compound and know the percentages and want to figure out what the formula is. So it's doing the exact same process but in reverse. The more common question is we want to know the formula from the mass percent. So in the problem, you'll be given percentages then you'll need to determine the empirical formula. Which is the lowest whole number ratio of the elements to each other. It's not very good then. If you are also given the molecular mass as part of the problem, you can then determine the molecular formula. So, as this implies, we are now going to do an example problem where we at least determine the empirical formula for this compound. Where this? Oh, it's on the back. everyone caught up. You screwed right there, sorry. Okay. So let's say we have the experimentally determined mass percents of an unknown compound. We then want to take these mass percents and turn them into an empirical formula. In order to do this, we make one huge life-changing assumption without which you cannot solve the problem. So for these problems, you have to assume that you have 100 grams. If you do not make that assumption, it is almost impossible to solve. Not impossible, but you've just made it really more hard on yourself than you should have. All right, so if I assume I have 100 grams of sample, and I know that 24.75% of it is potassium, how many grams of potassium do I know is in my sample? Exactly. So now I've turned these percentages into grams, which is super easy to work with now. So by making this assumption, I can now say that is 24.75 grams. This is now 34.77 grams. And this is now 40.51 grams. All right, so that was really step one, converting those percentages to grams. Step two is going to be I need to convert grams to moles, all right, because my empirical formula is a whole number mole ratio, so I need to be in moles in order to do this conversion. So how do I change 24.75 grams of potassium into moles of potassium? What do I need? I need to head over here and check out the periodic table. And since no one can see it, I'll just go ahead and rewrite what these values are. K is 39.09 grams per mole. Mn is all right, so those are the molar masses. So everybody take a minute and convert these grams using their molar mass into moles. Again, that should hopefully be a review. How many significant figures do I get in any of these? 4. I get 4. Everybody get something in that ballpark? All right, step 3 to these kinds of problems is now I have a mole ratio. I now want to figure out the whole number mole ratio between these 3 elements. So you divide each of the moles by the one that is the least number of moles. All right, so I have 3 different types of moles. Which one of the 3 is the smallest number of moles? This guy, the manganese, is slightly smaller. Very close, though. Right? 329 compared to 332. So, okay. All right, so we're going to divide all the moles by the least number of moles to get a whole number ratio. So for potassium, what whole number does that come closest to? Right? And you could do the manganese, I mean, for completeness, you could do that. Not really necessary. What whole number does the oxygen come closest to? When I did the division, what for? So what this tells us is that the potassium to manganese ratio is 1 to 1, and the oxygen to manganese ratio is 1 to 4. So I need 1 potassium, 1 manganese, and then how many oxygens? So for my unknown compound, I at least know that is the empirical formula of 1 to 1 to 4. All right, we're going to do one more of those, I've decided. So I didn't leave you a slide for it. So you have to just like make yourself a little side note or flip a piece of paper over it or something. All right, let's say I have oh, no problem. I think my math is off. Let me just double check this question real quick. All right, so let's determine the empirical formula for a compound that contains 70-ish% chlorine, 11.88% carbon, and 18.54% fluorine. So, with whoever you're sitting next to, let me at least give you the formula masses so you have those. Try for the next 3-4 minutes. See how far you can get in figuring out to the molecular formula. Remember to start with the assumption that you have 100 grams. Everybody gets something like that? 1 to 1 to 2? Yeah. you don't have enough information, so it doesn't really matter. Yeah. You could have written it anyway. You could have written it CL2, CF. That would be fine too. Yep. Everybody feel good at least about that part? Yes. There we go.
So, are you supposed to, how did you get 1 mole carbon?
How did I get this part?
Yeah.
I took 1.96 divided by 0.9763.
Yeah.
Comes to about 2-ish.
2-ish. And, so you don't go to the next highest integer, you just stay.
Whichever one it comes to closest, right? So like 1.963 divided by 0.9763. You get 2.0102. Yeah. Yeah. The other two turn out to be real close to 1. Yeah.
Second step, why do you erase the whole number and put, like, once you add that?
Because I was doing multiple steps in my head at once. It's more appropriate to do it in 3 steps, but in this particular case, it turns out to be fine to skip ahead to 2. I knew what the answer was, and so in my head I already knew it was going to be 2, but it's more appropriate to write down to have the significant figures and then divide it out, because it's not always going to be 1 to 1 to 2, or 1 to 1, so it's my fault. I was reading my Post-it note with the answer on it. I was skipping ahead. Other questions about that? All right, what if, all right, so this is the empirical formula. But we want to figure out what's the actual formula. Right, so that is good. I know for sure that it's a 1 to 1 to 2 ratio, but I want to go from empirical to molecular, the exact. So molecular formula is just a whole number multiple of the empirical formula. So let's say I have this example here. I have acetylene, which is used in welding, which is my retirement plan. After I retire from teaching, I really want to learn how to weld. That just sounds super fun, like making stuff. The little torch thing seems like you get the fun mask. I'm digging it. Anyway, that'll be my retirement hobby. I'll be the person making like metal sculptures that you can buy from me at different, craft fairs. That's my retirement plan. I'll be making these gigantic metal chickens that are really popular right now. That people put in their front yard, I guess. I don't know where you put a metal chicken, but really, really in. So, all right. So let's say I have to have acetylene because that's the gas used for welding. I know that it is 92.26% carbon and 7.74% hydrogen, and I also know its molecular weight. So it's 2 parts. We first figure out the empirical formula, like we just did for the past 2 problems, and then we'll add on a 4th step to go from empirical to molecular. All right, so first step is converting that to grams. I know the molar mass of carbon. Step 2, be converting those to moles. All right, so now that I have my moles, how do I figure out their ratio? 5 at least, or you can kind of eyeball it. What does it look like the ratio is going to be? 1-to-1, right? So I can say 7.74 mole of H per 7.682 mole of C means that that is the empirical formula, right? 1 carbon and 1 hydrogen. What would be the overall molar mass of a carbon-hydrogen molecule? Be 13 change, right? But I know that the overall weight is 26. So how do I get from 13 to 26? The easiest way. I double it, and I double both of them. So what is my accurate molecular formula? So this has a weight of 13 or so grams per mole. So it must be C2H2 to get to about 26. Ooh, sorry, I fell off the bottom of the page. Right, 1-to-1 is about 13 grams per mole. And I know it should be 26, so it should just be doubled. That's really an obvious example, right? I mean, 13 and 26, you can do it in your head. What if we flip back to that one we just had with the chlorine and the fluorine? Here it is. Okay, for this CFCl2, that's the empirical formula. Let's say I know that the molar mass of the final product is 202 grams per mole. What is the molar mass of just this by itself in its current empirical formula? I actually don't know. Let me see. Has anyone done it yet? You're just going to trust me? Okay. All right, CFCl2 is 101 grams per mole. And if I know its molar mass is 202 grams per mole, what is its correct molecular formula? That's it. So the hardest part is figuring out the molecular. Once you get the molecular, it's going to be some whole number multiple, usually a 2 or a 3. Maybe I'll go crazy on the test and have like 4. Probably not 2 or 3. To be honest. All right, how do I feel about that? Good? Confident? All right. Well, let's then go back to the slide I skipped earlier about conversion factors and molecular formulas. All right, so the chemical formula is what you can do it, molecular chemical formula, empirical chemical formula. Right, it contains within them the relationship between the atoms that make up the molecules. It's a whole number ratio of atoms. We're at the chemical formula. So if I say I have 1 mole of my go-to compound, right, I have 1 mole of that, how many moles of carbon are in it? 2, right? This is saying I have 2 moles. How many moles of hydrogen? Yep, 4 moles of hydrogen. What about oxygen? 2. Okay. Right, so if I have 1 mole of this, within it, it's 2 moles of carbon, 4 moles of hydrogen, 2 moles of oxygen. So now we can say, okay, I have this formula. and I have 50 grams of this molecule. I want to know how many grams of it are just carbon, using my brand new relationship. So we're going to start off with the thing that they gave us, 50 grams. All right, so this is a moles ratio, right? 1 mole of this, 2 moles of this. I'm in grams. How do I get out of grams of acetic acid into moles of acetic acid? What do you have to find? The molar mass, and I'm feeling generous today, so I'm going to go ahead and tell you. Ran out of space in my parentheses. 60 grams of acetic acid. All right, so now I'm in moles of acetic acid. I want to end up in grams of carbon. So what is the next step to get me on the way to talking about carbon? Right? We have this relationship right up here that's 2 moles of carbon for every 1 mole of acetic acid. And since I have moles of acetic acid on top, I must want moles of acetic acid on the bottom. Okay, what's the last thing I have to do? Now I'm in moles, but I want to end up in grams. So what relationship do I know about carbon? It's molar mass, right? So it is 12.01 grams for every 1 mole. Let's see what that turns out to be. 50 divided by 60 times 2. How many significant figures do I get to keep as my final answer? 3. Yep, from that. So 20 point looks like 0. So within 50 grams, yeah.
What's the bottom number in that first set of parentheses again?
This one?
Yes, ma'am.
That's the molar mass of this. Yep. So that's the mass of all of that together, and then that's the mass of just a carbon. So within 50 grams of acetic acid, I know 20 of the grams are just carbons, which then you could certainly turn to a mass percent if you wanted to, but we already did that. So. All right, I'm going to stop there to make sure you guys have enough time to do your quiz. We'll finish chapter 3, do some balancing equations next time. Yay, balancing equations. I'm just going to say it, I really hate balancing equations. I'm terrible at it. So I'm going to do my best not to confuse you. Sorry, it's my kryptonite.